So thank you everyone for joining. It's great to see a lot of familiar faces again. I'm going to talk about work that we've done with my team in Athens, as well as part of the team being in Belgium on an EU-wide capacity expansion planning model. So I'm going to give a bit of policy context and spend a bit more time here because I think that's one of the more interesting parts, then give some technical details on our implementation, discuss results as they were presented to Atlanta and before that in Spain. But then I'm going to also show you some ongoing activities the last couple of weeks that are quite exciting, and then conclude. So first, a comment on the context. So I don't need to motivate this for this crowd. We have aggressive renewable energy integration targets in Europe. So the issue here is that, so on the one hand, yeah, the targets are very aggressive and they are becoming even more aggressive as we move forward, as reflected, for instance, in the European Green Deal, which is more aggressive today than it was in its original goal that was set in 2014. We have done incredible things so far in terms of renewables integration, but we still have a long way to go if we're honest about net zero systems. And we also have a remarkable progress in the integration of renewables. Despite the best efforts of the US government, we're still on quite a good path to integrate a massive amount of wind and solar power. And this is also related to the economics of these resources, which have exhibited tremendous declines over the years. You also know all of this, but I'm just going to repeat the stuff that we are interested in. So renewables introduce exotic challenges. The ones that we are discussing a lot in our conference relate to uncertainty. And one that I think is particularly interesting for this assignment is the fact that where we locate renewables is a function of weather, so favorable winds and nice sun. Where we had located in the past transmission lines was a function of where we had located thermal plants, and that was a very different consideration, which means that our networks are not in a position right now to absorb all these renewables. So there's an issue of binding network constraints, and this is the underarching theme of the talk. This is an example of uncertainty. The slides are more than 12 years old, which is starting to become embarrassing, but this was California in 2005. Yeah, it's worse. It's 20 years. I need to review these slides. Now, the institutional context that I think is very interesting. So here I present the typical blueprint of a typical electricity market that you might encounter somewhere in the globe, and I'm interested in this. So the nodes here are the market participants. The arrows are the commodities or services that are traded. So I'm interested in this entity, the generator, who has three possible revenue streams: energy, reserves, or capacity markets. So I'm going to focus on capacity markets, which Elena anyway gave you a great discussion about today in the morning. And I want to specifically talk about the intention of the European Commission, possible intention to put in place a renewable capacity auctions. Before I actually say more about this intention itself, I forgot to talk a bit about the team composition. So this is work that's been done with Danielle, a former PhD student of mine, Alexandros, who's now working on the extension of Danielle's work, Marilena from our team in Athens, but also importantly, Georg Thomassen and David Pozo from the JRC of the European Commission based in Nispra. So this assignment has been given to us from the Commission, and the question is how to design renewable energy auctions that are targeting renewable assets and rewarding them for being located in specific, and the interesting aspect here is you get technology-specific capacity auctions, but also nodal resolution, which in a way is also an admission of the European Commission that zonal pricing has failed. As a simple example of that, think of being an investor in Wind, in Germany, you have a few million euro to allocate, and you can't tell the difference between north and south based on a zonal German price. So what the Commission has in place, despite the fact that there's clearly congestion from the north to the south, so the remedy for the Commission is a correction to zonal pricing through renewable auctions. So our task is basically to run these at EU scale and figure out, with nodal resolution, and figure out under different climate scenarios where to invest today to be able to deal with tomorrow's network constraints. Now, this work falls under the umbrella of a broader institutional and modeling effort, and I'll explain to you how we got here as a team. So as I mentioned, this is the group of people who are working on this, and the model we are working on is quite similar to the European Resource Adequacy Assessment model. I'll say 2 words about that in a moment. Now, the first time we got our hands on the ERA, the European Resource Adequacy Assessment model, was when Daniel was still a PhD student in Louvain, where I was a professor, and he did a summer internship at ENSOI, and he was able to solve a version of ERA with 35 scenarios, although the Plexus model that ENSOI was using up to that point was limited to 3 scenarios. So that got us in the game. And then what's interesting is that the JRC uses similar models to the ERA. It's also done for flexibility assessment, so it's a standard modeling framework for a variety of exercises. And what Marilena is doing in her PhD is integrating endogenous reliability metrics into the capacity expansion model. And what we are doing in this work is endogenizing renewable integration targets into this model. But the important message for you here is twofold. One is we're using the standard capacity expansion model that the Commission is interested in using, and also we're working with the Commission on this, so it becomes institutionally relevant. Now, ERA is part of a broader policy process, so Regulation 943 of 2019, in paragraph 43, mentions that the ENSOI for electricity should carry out a robust medium to long-term European resource adequacy assessment to provide an objective basis for the assessment of adequacy concerns. In simple English, what this means is that if you, well, let me finish reading. The resource adequacy concern that capacity mechanisms address should be based on the European resource adequacy assessment, and that assessment may be complemented by national assessments. This means 2 things in simple English. First, if you want a capacity market in your country, you have to demonstrate that through an ERA-type study. And in order to avoid every country doing whatever they want, we centralize this through ENSOI. These are the 2 relevant messages here. So the overall cat and mouse game that the regulators are playing with the transmission system operators is depicted in this slide. ACER, as the police, provides guidelines for the ERA methodology, approves it, approves the reports generated by ENSOI, and provides guidelines, that's the end game of the TSOs, for determination of reliability criteria of member states. ENSOI formulates the methodology of ERA and executes the model, and the national TSOs are basically involved in the ERA. They perform their own adequacy assessments on top of the ERA to make sure that national considerations are accounted for. They justify deviations from ERA and identify a gap of capacities, because if you identify this, then you justify in the eyes of DG Comp a capacity mechanism for your country. And the nature of the cat and mouse game here is that TSOs, of course, want more capacity. It makes their system more reliable and their life easier. And at the same time, they're not paying for it. So that's where you have to be careful about how much capacity they're asking for. And that's why the police is here to monitor the whole process, with ERA being a hopefully objective basis for that. So the stochastic programming element in this story is that when we're doing this ERA model, we are essentially looking at climate years. So standard macroeconomic reasoning leads you to the conclusion that if you want to know what the market will look like in, for instance, 20 years from today, under a risk-neutral setting without strategic behavior, blah, 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 the usual assumptions, the outcome of that market is captured by in its simplest form, a 2-stage stochastic program. And therefore, the question that this kind of model is answering is, what can we expect the market to deliver in a few decades from now if we have an energy-only market and if we have climate uncertainty? And that kind of brings stochastic programming into the door of all of this. And the actual model, the way you can think of it, is a classic two-stage stochastic program where we expand first and then dispatch for 35 different climate years. Now, this same model, which has become so institutionally relevant, is the one that we are using, but posing a different question. How do we integrate a lot of renewables into a system that we're looking a few decades from now, and we're worried about climate uncertainty? When we're talking about network congestion, of course, we need to worry about power flow. I expect this audience to be very familiar with this concept. So we are working with the linearization of Kirchhoff's current and voltage law, which implies that there is a linear mapping between net injections in the power grid and line flows. And this actually creates the interesting challenge that we can't decide how the power is routed over the network. It's rather determined by power transfer distribution factors, which tell you how much a given line on the network is loaded if you inject 1 megawatt of power in a reference node and extract it at the hub node. So we're using a standard DCOPF based on power transfer distribution factors. But this, from an operational standpoint, captures a challenge. If you think about it, it's quite complex. You have to decide today where to put a renewable plant. There's 35 different things that could happen, which imply 35 different routes of power over the European grid. And you want to make the maximum use of your investment depending on where you put it. That's the optimization challenge. So I'm going to talk to you more now about the model. It's European coverage. It's hourly time resolution. We linearize power flow equations, as I just mentioned. We deal with several climate scenarios, and we decide on both assets to build and where to build them, but only for renewables. This is why this study is targeted for renewable auctions. And what's really interesting from an optimization standpoint is that we are dealing with a target expected volume absorbed of renewable energy. And I'll show you mathematically what that means in a moment, but it's a bit exotic compared to textbook stochastic programming. How do we cope with the scale of the model? We rely on decomposition methods to break up the problem into smaller pieces, and then access to high-performance computing infrastructure to solve the decomposed problem. This is the standard textbook description of a capacity expansion model. No surprises here. We have a two-stage decision process where we invest first, and the first stage decisions are depicted in red color. That's the X variables, how much we build of each technology. And the second stage decisions are depicted in the blue variables. P is for energy production, LS is involuntary load shedding, NE is net injection of energy in a given node, F is flow, phi is the angle of the voltage phasors. And first stage costs are costs of building renewable infrastructure. Second stage costs are expected costs of operation. And the capital omega here is the set of 35 climate scenarios. Your second stage costs are related to dispatching conventional assets as well as involuntary load shedding. You cannot invest more than a certain upper limit per technology. You can't produce more than what you've invested. The net injection at every node is the demand minus the production, and load shedding also implicitly acts as production. And what you inject in a given node is what's going out into the network. And the linearization of Kirchhoff's laws is the standard B theta formulation, and these are the line flow limits. So this is the setup, and the red marks first stage decisions, the blue marks first stage constraints and objective function terms, the blue marks second stage constraints and second stage objective function terms. This is standard textbook stochastic programming because the scenarios are all implicitly coupled together through the constraints that connect second stage decisions to first stage constraints. So one can use here standard decomposition methods like cutting plane methods, which is actually our foundation. What's exotic about the problem that the Commission wants to solve is that if I, as a regulator, decide that throughout all of Europe, I want TV, terawatt hours of renewable energy absorbed in expectation, that implies an expectation over renewable energy absorbed, which is a direct coupling of the second stage constraints through a summation as a constraint in the model. And that's a direct coupling between scenarios, which is exotic. It's something different. So how do we deal with that? Very nice work by Jacobson, Pesci, and generally the team of Jenkins, either his own PhDs or Europeans who were visiting his group a few months or years ago. Yeah, years ago. Their idea is to use budget variables, and this allows us to convert the model to standard two-stage stochastic programming form. And here's how the trick works. You can't do cutting plane methods on this. The whole idea of cutting plane methods is you get a value function given your X first stage decision, and that's the only thing that affects the second stage. Here, the second stage is directly coupled. So their thought is, well, why don't we translate this to something that obeys the original grammar of this algorithm? So why don't we introduce a Q omega variable, which is how much renewable I want to use up in a scenario omega, make this a first stage decision that's solved in the master, and this is then injected as a first stage decision to the second stage problem. So the strategy here is that you make these Qs red, so first stage decisions. They become explicit first stage constraints, the target volumes. And then the Qs show up also in second stage constraints as right-hand side parameters that you fixed through decisions in the master. So it's a very clever idea to bring the problem back to a structure that we can deal with. Now, once we have that, then the strategy will be to use a master to solve for first stage decision, and then slave sub-problems to solve for second stage of dispatch. And these first stage decisions now involve not only what I'm building and where I'm building it, but also how much renewables I'm using in every scenario of my system. So this is the cutting plane idea applied to this strategy. So we have the optimality cuts of value functions, which value functions, however, now are value functions of these two first stage decisions. So what technology mix I'm building and where I'm building it, as well as how much renewables I'm using in a given scenario. And one can directly implement benders to this overall setup. So now these, optimality cuts, as I mentioned, they implicate both X and Q. And for every scenario, now we can do scenario decomposition where we're essentially solving an economic dispatch which says I've committed to this mix of renewables throughout my system, and this is how much renewable energy I want to use in that scenario. As the usual guarantees hold, so every iteration of this process gives you a lower bound through the master, and every iteration also gives you an upper bound by collecting the cost of what you've done in the second stage for a given choice of trial investment, and you can loop this towards convergence. So the overall scheme looks as follows. We solve we start with an initial lower bound for the value function so that the thing is bounded. We get candidate investments. We solve the slaves by dispatching for a given choice of investments and renewable target. We check if we've converged because we get upper bounds from here and lower bounds from here. If not, we add optimality cuts to the master and we continue. Now, this is not the kind of thing you can use for solving the problem at the scale that we want to solve it because it's bouncing around too much. The original cuts are too unintelligent. They go in the corners of the feasible space. On top of that, the slaves in such frameworks are supposed to be fast. And here we're solving an economic dispatch of all Europe with all of its network with hourly resolution. And that's very heavy. And then also we have a ton of computers in GRNet, in our high-performance computing cluster, and we can't use them because if we only have 35 scenarios, we can only use 35 parallel processors. So the question is how we overcome these issues. The first comment is how we overcome the instability of the cutting plane algorithm. So here the idea is that you want to stabilize the process by keeping track of good first stage candidate decisions and not moving too far away from them through standard regularization techniques. How do you initialize this? What you can do is you can pick the average of the wait and see solution to warm start the whole process. And then what you do to regularize is you put L2 penalizations on moving away from XV, QV, which is your current candidate first stage decision. And this is now a quadratic convex problem. It's small, at least for a few iterations, so you can still cope with the fact that it's quadratic. And also, there's things to do on cut selection that I'll talk about towards the end of the talk today. Standard textbook approaches for updating the regularization parameters. And also, as I mentioned, we start the whole thing from an XV, QV, which is obtained as the average of the wait-and-see solution, so that we start from a good point and then move around from that point, but in a stable way, not by going to the corners of the feasible space. Now, this also means, however, that when you're solving the regularized master, you're breaking bounds because you have these quadratic terms, so you want to resolve the master to also get lower bounds, and the overall scheme now looks like this. So we have a lower bounding master to get lower bounds. To that, we add a regularized master to get the new iterate. Then we solve the slaves. And if we haven't converged, then we check if our new first stage decision is better than the previous one, in which case we update the eligible first stage optimal solution. And if we haven't improved, then we keep the old one and we repeat the process. So that takes care of the instability of the benders. Now the question is how we deal with the second stage being an annual economic dispatch with hourly resolution for thousands of nodes. So here, the idea is to break the problem into blocks of time. And therefore, your subproblems now become what happens in scenario omega in time block tk. I'll say more about that in a moment, but before I say that, why do we worry about the economic dispatch in the first place? Why is it time coupled? The issue is that we're modeling all of Europe, which, as you know, and as we saw in the previous session, has some long duration hydro. These are multi-month couplings. So production of hydro enters in the power balance constraints and also in the energy reservoir dynamics, and there are upper limits in these energy levels. So the whole thing becomes coupled over the whole year. And how do we cope with that? We break the overall time horizon into a set of capital K blocks of time. Each little k block of time has a set of periods, capital T subscript k, and then we dispatch for that subperiod. When we're doing that, the issue is that we have to somehow stitch the blocks between each other, and for that we introduce these auxiliary energy level variables. And what we say is that these energy level variables, which say at what energy level you will start for block K and at what energy level you will end for block K, those two become first stage decisions. And then the overall trick is playing again this Jenkins concept of not deciding just X, Q, so how much renewables you use in scenario omega, but also for every one of your storages, where you start your storage at the beginning of block K and where you end. And this is it, basically. So the question is how this modifies the overall scheme. Actually, a couple more comments on these sub-problems. We put penalties on violating these energy levels because once you do this maneuver, you can create sub-problems that are infeasible in the sense that your energy storage levels are so difficult that the second stage is infeasible. You could say, why don't you use unbounded, basically feasibility cuts? The answer is that the slaves, we want to solve them with interior point. We've found that solving them with simplex is basically too slow. So we can't get rays of unboundedness for the dual, so we cannot get feasibility cuts. So instead of that, we use these slack variables to penalize, and that way we can continue using interior point with Gurobi, which is fast enough for our needs. That's kind of an empirical observation. And now what's really cool is that where we could decompose before per scenario, we can also now decompose per time block. And that's very helpful because it really allows us to first chop up the second stage into very small pieces and also use all the computers that we have at our disposal. So what does the overall algorithm look like now? Note the introduction of energy storage levels as explicit first stage decisions now. And therefore, since they are since they are first stage decisions, first of all, they're implicated in the optimality cuts. And on top of that, they become part of the regularization. So your first stage vector now is x, q, e. And your moving away is penalized with L2. That means also penalizing the energy deviations with L2. The overall scheme hasn't really changed fundamentally. The only thing that has changed is the structure of the slave subproblems. But now where you had 35 climate scenarios, so kind of a horizontal chopping of the whole block, you also chop it vertically because you chop it over time. And that really effectively deals with the third problem as well. If I have 15 scenarios that we're solving for this capacity expansion model, but I chop up a year into 52 weeks of hourly time step, that means I have now 780 subproblems. And that means that if I have access to order of 1,000 CPUs, I can really make good use of them because I send one subproblem k, omega to each of the CPUs. And that's exactly what we end up doing. So we basically have one CPU allocated to the master, and then we're allocating blocks of time within a given scenario omega to the second CPU, and another block of time, the third one, until we finish with the first scenario. Then we move to the next scenario until the 15th scenario. So that's how the work is allocated in the cluster. And that allows us to access, exploit our access to hundreds of CPUs, which is what GRNet allows us to do. So, results on this part. This is no news compared to Atlanta. It's just that in Atlanta I said all of this in 8 minutes. So, so we do CWE. The Commission wanted us to solve all of the EU. And we weren't able to do that within the horizon of the project. But we did tackle CWE. That's France, Germany, Luxembourg, Belgium, Netherlands, Switzerland. That's the dark part here. It's 40% of EU load. We wanted to ideally solve also the rest. We modeled the transmission network at nodal resolution, 1550 nodes, B theta formulation for linearized power flow. Our data source is PIPSA, unit-based thermal generation model with 918 generators, no unit commitment. PIPSA is our data source. Hydro is 3 types of hydro: reservoir, run-of-river, pump storage. We have 121 reservoirs, 66 pump storage, 367 run-of-river. Also the source is PIPSA. About 1,500 gigawatts each of solar and wind to integrate. PIPSA for the candidate locations, and ENSOI transparency platform for the climate data. Uncertainty, the climate scenarios that are 15, and this is sourced from ERA, and we have one target year as opposed to multi-stage modeling, which is something that I think Acer and the Commission are a bit interested these days. We use 100 CPUs that are available on 25 nodes in GRNet, the Greek national cluster. We have 56 gigabytes per RAM per node, and we allocate about 7 subproblems per CPU. So the way it's done is CPU 1 takes the master and 7 subproblems, CPU takes the next 7 subproblems up to the 100 CPU. So what ends up happening is, since we have 600, we break up the time not in weekly time steps, but we aggregate a bit more to 46. So it's something a bit more than a week. And that means that if we have 700 CPUs, that's almost 7 subproblems per CPU because we have 690 slave subproblems. This is the performance. So we have upper bounds dashed black, lower bounds also dashed black. and the relative gap in percent is the red. This is zoom in of what's happening here. This is what we could do a few weeks ago, where we reach about 3% optimality gap. And we do that in 60 iterations, where, not 60, in 80. But after 60, it's really only the lower bound where we're doing extra work. The upper bound more or less stabilizes. This is how the investment mix converges. It takes a while, so around 60 iterations, whereas the renewable energy mix, the Q variable, stabilizes much faster than that. And I guess, what's happening in the beginning is the algorithm is really struggling to figure out where to put stuff. Although it's deciding early how much to use per scenario, it's struggling to figure out where to put things. And in terms of elapsed time, the same figure as you saw earlier, but not in iterations, rather in run hours. So we run these 100 CPUs in 30 hours, and the average time per iteration is about 20 minutes. This is what was killing us, and still is, actually. We're working on it, though, in the stuff I showed in Atlanta. So this is the time, this is evolution over iterations and runtime. The yellow is time consumed by the slaves. Okay, in the beginning, obviously, it's the bulk. The dark red is the lower bounding master, and the light red is the regularized master, the one you need to go to the next first stage iterate. And that one is a quadratic program, but it's getting bigger and bigger because we're adding optimality cuts as we go, and this is really killing us. That said, let's see what we do in the CWE. So we record the wait and see, so the expected value of perfect information. You want this to be non-negligible if uncertainty matters in your problem. We document an EVPI of 3.6%, which means that if we had a crystal sphere and we could adapt the investments to the climate scenario, we could shave 3.6% from costs. Why do we do that? Where is the uncertainty hitting us? To get an answer to that, we can look at how much wind and solar is being invested in the stochastic solution and in the wait-and-see solution. So this axis here is in gigawatts. You see that both models build more or less the same amount of solar, but the stochastic programming model is more conservative in how much wind it builds. And this relates to what I said earlier. If you have the luxury of adapting where you locate wind assets to the climate scenario, you're going to build less of them and still achieve the same total volume target. But if you don't know which climate scenario will hit you, then sometimes you have to shed renewables. And that's what's happening here. So here I'm depicting the production shedding in terawatt hours, and you can see that the stochastic programming solution is shedding more energy than actually it's producing more energy than, so this is not shedding, this is renewable energy produced, and all of this is being shed because the stochastic programming, the perfect foresight model is using all of the renewable energy that is producing, and this excess for the stochastic programming model is never used, so it's being thrown away, which is an inevitable consequence of the fact that we don't have a crystal sphere, but it's still the best we can do. Now, what have we been doing since Atlanta? So Alexandros is the one to thank for all the work I'm about to show you now, and then I'll stop talking and we'll discuss. I have 40 minutes, right? Yeah, okay. So the first thing we've done is introduce a level algorithm to the model. So regularization is one way to stabilize cutting plane methods, but it's not the only one. And actually another one which is super effective is the level algorithm. What the level algorithm does is it says, listen, if you are somewhere here and you have a cutting plane model of a value function, and the true value function is the black one, and your cutting plane model thinks that the value function is the red one, rather than jumping over here, which is very unstable, consider this level set, which is the set of first stage decisions that'll keep you under a certain level, and go from here where you are right now and project onto that level set. And that generates a much more stable behavior. But in doing that, you have to be taking mixes of what is your lower bound from the master right now, plus what the oracle tells you is the upper bound. So if you take a 50-50% mix, then the level that you want to target with the red function is somewhere in the middle here, and the level set that achieves that is some black set that looks like this. You project onto that set, and you continue making progress. And that really stabilizes the thing, because you can see you're making small steps every step of the way. You're projecting onto this black set, which is honing in on the optimal solution. So that's the geometry of how this is working. And this is what this means for our master problem. I don't want to overwhelm you with the details. But the way this is structured is that here we have the actual master problem, and here we have the level set problem, which is basically projection. This projecting that I mentioned to you earlier is you can pick from a bunch of first stage decisions. There's a bunch of implicit constraints that tell you that you have to stay below this value function level. So find me, starting from point x star, q star, e star, the closest point in the set here, the level set, that is the point that is closest to this x star, q star, e star. So that's a QP, but it really stabilizes the algorithm. And the way this all ends up working is you have your master, which you use to generate a lower bound. You then use the level set, which also accepts as input the upper bound, because that's how it decides what's the new level. And the level set problem, which is this QP that I just mentioned, gives you the first stage decisions. The slaves then take these decisions, compute their optimal solutions, and that allows us to generate new cuts using these lambda multipliers. And it also feeds into an upper bounding procedure, and the whole thing iterates. So it's not regularized. It's not regularization through L2 norm. It's rather regularization through level sets. Now, what does this do for us? I'm showing you CWE again. I'm showing you again total cost, upper bounds, lower bounds, and then evolution in hours, but also evolution in iterations. And keep an eye on, so first of all, the thing stabilizes after 9 iterations. That takes about 3.5 hours. And what's interesting is this here, because Daniel was achieving 3% optimality gap. And already with this trick, we've brought the optimality gap down to 2.46% with comparable runtimes and CPUs and iterations. On top of the level set idea, you can do a dynamic adjustment of this level set. The idea here goes as follows. If I'm just, if this thing is not, what is it? So, let me remember the idea. So, yeah, if the upper bound is not moving a lot, then it probably means that this line here is way too close to GK best. So you can pick, and that's a result of how you pick this lambda, this mixture between GK best and theta K best. So I can pick this lambda to be almost equal to 1. It means I'm kind of, eventually the thing will get the right answer, but it's decreasing the upper lines very, very slowly. So you're moving very, very little here. So if you're observing that in your code, that you're moving your upper bound very little, what you want to do is maybe become a bit more aggressive on the lambda and bring it lower than something very close to 1. And that's the philosophy of this idea of monitoring how your bounds are moving to decide how aggressively you adapt the mixture of upper and lower bound to get the new level set. The actual algorithm that's done for doing that is this, but I'm not even going to attempt. I was looking at it in the airplane for a couple of hours, and finally I think I made some sense of it, but I don't have time to explain that process to you now. But what I can report to you is the following. It really helps us. So, by the way, this is in Thomas Gard work and colleagues. I have the reference in the end of the presentation. Now, what this does for us is it tightens both the upper bounds and the lower bounds. So the blue and the orange are the just level set. The dynamic level set is the green and the red. So you see improvements on both fronts. I'm depicting both in terms of elapsed time as well as iterations. And actually, what we are then achieving all of a sudden with this approach is in the same runtime and approximately the same number of iterations, we now squeeze We started at 3%, we went to something like 2.4%, and we now go down to 1.86%. So that's 0.6 better than the previous best thing we could do. So that's very useful. And what's still hurting us is the blue stuff here. So these are the lower bounding masters. I think the labels might be wrong here, so that was the QP. Anyway, one of the two masters is really slow because it's adding optimality cuts and growing bigger. And yeah, so that's still an issue. So to deal with this last issue, this looks more complicated than it is. We do adaptive cuts. What do adaptive cuts do for you? I'll keep this slide here, but ignore the complexity. The idea is fairly simple. You have cuts, and if your cuts have not been active for a long time, you just basically... first, before I say that, standard benders without multicut is hopeless in these things. It's going to take forever. So we do multicut. But multicut means you have one cut per omega. Now, if it's taking if these cuts are not active for a long time, you just take them and merge them into a single approximation of the v of x function as opposed to the q function, the q omega of x. And that's all this is saying. But what does that do for you? It decreases the size of the master again, because the master is killing us as our iterations are progressing, and this too becomes very effective, and I'm out of time, but what is the end result is we now are able to squeeze the optimality gap to 1.28%, and I'll stop there. That's a bunch of useful tools you can consider maybe in your work, and of course we're open to suggestions for other tools as well. Thank you.